Hello and welcome to PHP Performance 1, everything you need to know about opcode caches from Engineering. My name is Davey Shafik and I'm a community engineer here at Engineering. I'm the author of the Zen Certification Study Guide as well as SitePoint's PHP Anthology and PHP Master Books. I'm a contributor to Zen Framework 1 and 2, PHP Documentation, and PHP Internals. And you can find me on Twitter as @dshafik. So what are opcode caches? Opcode caches are performance-enhancing extensions for PHP. They transparently inject themselves into the PHP execution lifecycle and cache as much of it as possible. It's pretty typical to see a 300% performance increase just with the default settings. The most common question I get asked is when should I use an opcode cache? And the answer is pretty simple. Always. Whether it's your development environment, your production environment, or somewhere in between, there really is no reason not to use an opcode cache. Installation is really easy and it's super easy to configure, and it pretty much just works. Now there is one major side effect that you might run into. It's what's known as a cache stampede. A cache stampede occurs when your cache expires while under a heavy load, and this is a problem that actually affects all caches. It's not just specific to opcode caches. There are a number of reasons your cache might expire, whether it's restarting the web server, data edits invalidating the cache, or maybe you're adding a new instance to your cluster so you can scale to handle the load and its local cache hasn't been created yet. It could also be something as severe as hardware failure. Whatever the cause, because you do not have a cache, you can neither sustain the amount of traffic or rebuild the cache. We'll look at how you can mitigate this issue later on. The next question you should be asking yourself is which opcode cache should I choose? Prior to PHP 5.5, the dominant opcode cache was the alternative PHP cache, or APC. However, with the release of PHP 5.5, Zend open sourced their proprietary Zend opcache and contributed it to the PHP project. Zend opcache is enabled by default for PHP 5.5 and above, and due to optimizations it does on your code when creating the cache, it performs between 6 and 100% faster than APC. APC is known to have issues with PHP 5.5, so if you're using PHP 5.3 or 5.4, you can choose either option, but moving forward from 5.5, we recommend that you only use Zend opcache. Next, we're going to talk about installation. Each of these extensions is available via PECL, which means they all are installed in very much the same way. Let's start by looking at Zend opcache. To install, you simply call PECL install Zend opcache beta. Then we need to add some configuration to our PHP INI, as shown here. First, we enable the Zend opcache using Zend extension, and then we have a number of different configuration options for the opcache. These settings here are taken from the manual and are considered to be a good baseline for optimal performance. You may need to tweak these options, and there are other options not shown here. Once you've made those changes, simply restart PHP, whether that means Nginx and PHP FPM or Apache. Now your code will be cached, as it is called. For APC, as I said, it's pretty much the same procedure for installing. Call PECL install APC beta and add the configuration shown here. This configuration is much simpler. We just need to add the extension and then enable the opcache. There are a number of other options available to change the behavior of the opcode cache, which I recommend looking into. Again, once you've made those changes, simply restart PHP and you're done. Last, there is APCU, which is optional. Again, very similar, PECL install APCU beta and add the configuration and restart PHP. One important thing to note is that I'm setting the APC serializer option to PHP to avoid a known bug in APCU. Also, make sure you don't try to use APC and APCU together, as that won't work very well. One other thing we're going to install is the Engineering PHP Performance Tools. This is a suite of tools to help you diagnose and improve the performance of your PHP applications. They are open sourced under the Apache 2 license and available from GitHub. They can be easily installed using the Composer package manager. To install the PHP Performance Tools, just add the repository to your composer.json as seen below. Set the engineering/PHP Performance Tools package as a requirement using debmaster for the version. Once you've made that modification to your composer.json, run composer update engineering/PHP Performance Tools to install the package itself. So as I said earlier, the primary problem of using caches is cache stampedes. There is, however, a simple way to solve the problem, known as priming the cache. While caches are normally built up as users access the site, during a high-load scenario, the idea behind priming the cache is to automatically fill up the cache as quickly as possible so your users can start using it. Now, unfortunately, with the Zendoc cache, there is no built-in method for priming the cache. This may change in PHP 5.6, but as of right now, that functionality isn't available. To solve this problem, we must automatically make web requests to our own web server. There is, however, a problem with this, which is that the server is already straining under the load. However, this method also primes your HTTP caches, for example, Varnish or Squid reverse proxies. To make this request, we can reuse our integration testing suite, but I know most of you probably don't have one. So instead, we have created a simple spider as part of the PHP performance tools called Cache Primer. Cache Primer is a simple HTTP spider that can perform multiple HTTP requests, either in parallel using PECL HTTP, or if that's not available, it will perform them in serial, which is obviously much slower. Cache Primer is easy to configure and use. The first thing we're going to do is to create a config.php in the current working directory. This is a simple PHP script that returns an array containing two keys. The first key is URLs, which is a subarray of URLs to Spider. You'll notice that for the example, I have intentionally added an invalid URL so that we can see what happens when we run the cache primer. The second key is threads, and it's an integer value indicating the desired number of concurrent requests you'd like to make, in this case, 3. If you do not wish to make parallel requests or don't want to use PECL HTTP, just set this value to 0. If PECL HTTP is not available, then the value is simply ignored. Next, because we installed with Composer, the cache primer binary is symlinked into the vendor bin directory. To run the primer, just call the cache primer binary in the same directory as your config.php. As you can see in the output, we are attempting to cache 4 URLs using 3 concurrent requests. We were able to successfully request 3 of our URLs and encountered 1 error in 0.6 seconds. This might seem quite slow. However, let's scale that up a little bit. Here we have 104 URLs to cache, and using 10 concurrent connections, we're able to complete that in just 4.6 seconds, which is a lot better. Next, let's take a look at APC. APC has built-in tools for priming the cache. It still requires a single HTTP request. This is because we have to prime the cache in the context it's going to be used. That is, you cannot run this on the command line and have the cache be available to the web server. However, because of the built-in functionality, we can cache any valid PHP code, whether it's behind a login, differs per locale, or is something like a partial view template. Any valid PHP code can be cached. Also, it's important to note that the code itself does not run. It is simply compiled and cached. Again, we have provided a tool for this called APC Primer. Using the APC Primer is a little more complex than the cache primer. The APC Primer provides basic HTTP security. However, we recommend not relying on this. Instead, you should integrate it into your admin control panel or as part of your build process, where you might upload it to a random URL only accessible to you, make the request, and then remove it again. The APC Primer uses the built-in APC compile file function to add the PHP code to the cache. There are alternatives to this method, but they are buggy. An APC compile file does everything we need. To use it, it requires that you place a small wrapper in a web-accessible location that simply requires the apc primer.php from the vendor directory. The APC Primer will cache all .php and .phtml files not located inside a test directory, because we obviously don't want to fill our cache with our unit tests. Again, as with the cache primer, we're going to create a config.php, which will reside in the same directory as the wrapper script. The first thing you see here is that we created a shortcut constant for the directory separator constant. Next, just like with the cache primer, we return an array with 2 keys. However, this time, the first key is the authentication configuration, which again, we recommend against using. And then the second key is the paths, is an array of paths in which to search recursively for files to cache. In this case, it's a Zen Framework 2 project, so we're going to cache the config, module, vendor, and public directories. Next, we place a simple wrapper within our web root. Here, for example, I'm placing it in the admin subdirectory as apc-cache-primer.php, and all it does is include apc-primer.php from the vendor directory. apc-primer.php will include the config.php unless you manually define a $config variable prior to including it. Now, to run the primer, we just request the file via HTTP, and as you can see here, we have cached 4,841 files in just over 2 seconds. This includes the entirety of Zen Framework 2, as well as all the other dependencies and the application code itself. Now that you know what opcode caches are, when to use them, and how to handle cache stampedes, we're going to look at how they work under the hood. The first thing we have to understand is the execution lifecycle of PHP. Very often PHP is referred to as a non-compiled language, as opposed to a compiled language like C, C++, or Java. This is actually a misnomer, because PHP is actually a compiled language. It's just that it happens every time you execute a script. This execution process actually looks a lot like Java. Let's take a look at the lifecycle of both of these languages. First, we'll look at PHP, shown here on the left. With PHP, when code is executed, we first parse it, turning it into a bunch of tokens in a process known as tokenizing. These tokens are then compiled into opcodes that are then passed into the Zen engine, where they are executed by the Zen virtual machine, giving us our output. For Java, on the right, rather than executing the code, we instead compile it using the Java compiler. Again, we have this parsing phase, the output of which is compiled into bytecodes, and then instead of passing it directly into the JVM, the Java virtual machine, we store the compiled code as a file. Later, to actually run the file, we pass the contents of that file, the bytecodes, into the JVM, where they are executed, giving us our output. The biggest difference between the two is that with Java, we are saving the state of our compilation process for later reuse. When we add an opcode cache, we are effectively doing the same thing, except instead of storing it in a file on disk, we're storing it in shared memory, and each time the code is run, we verify we have the latest version, and if not, recompile and cache again. Looking at the lifecycle now, when we execute, we check the opcode cache to see if the code has been cached already, and that we have the latest version. If it hasn't been cached, we parse it into tokens, compile it into opcodes, and then in the case of Zen opcache, we perform multiple optimizations on those opcodes, and then finally store it in the cache in shared memory. If it has been cached, we simply retrieve the stored opcodes from shared memory, which is super fast, and in both cases, we then feed the opcodes to the Zen engine for execution and output. So you can now see where our performance increases are happening. I have mentioned two different representations of your code seen during the execution lifecycle, tokens and opcodes. To explore these further, I'd like to start by showing you what I consider to be the world's worst hello world. This is obviously an over-engineered hello world, but we are doing something very simple in a complex way to effectively explore the parsing and compilation process more. The first part in the process is tokenizing. This is done when parsing. This is simply a way of breaking down the text that is your code into a semantic representation that can then be compiled. When we tokenize our example, we end up with this. You will notice several things immediately. First, that it is fairly logical in the way it breaks up the code. Second, that each token is given a name starting with T_, except for tokens which are a single character, braces, parentheses, quotes, and semicolons. This is because it's more effective to simply store those characters than the token name value pair. These T_ names are also where the infamous T _neku doteum error comes from. It is thrown when the double colon token is encountered unexpectedly. You can get the tokens for any code using the tokenizer extension, which is included with PHP. It is often used for static analysis tools. One thing I want to draw your attention to is the different tokens generated by the two strings in our code. Both of these strings are double quoted, however, one includes a variable, $2, for interpolation, while the other one does not. When this is tokenized, the interpolated string results in 4 tokens, the opening quote, the static string hello, the variable, and the closing quote. The non-interpolated string, however, results in a single token, which is the quoted string world. Looking at this, we can start to see why this matters from a performance standpoint. However, Don't get caught up in these micro-optimizations, like single versus double quotes or post versus pre-incrementing. Zen.cache will also automatically optimize most of these kind of things anyway. Finally, we're going to take a look at the compiling phase. To do this, we're going to use VLD, the Vulkan Logic Dumper. This is an extension to dump the compiled opcodes and is again available by Peckle. To install, just use peckle install VLD beta, add the extension equals vld.so to your PHP INI, and we're ready to go. To use VLD, we do so by passing a couple of INI flags to the command line, along with the file to dump the opcodes for. These INI flags enable VLD and disable actual execution of the code. We do it this way so we don't have to keep modifying our PHP INI with these settings to be able to use code normally. VLD will dump the opcodes to the terminal, and it does so in a specific order. First, it will dump the global code, known as the main script, followed by global functions, and finally class functions. These dumps can be pretty confusing to look at, but they're pretty simple once you know what's what. You will get a complete dump for the main script, and then one for each global or class function. Each dump starts with the header section. This will show, when appropriate, the class name, function name, and file name, followed by the function name again. Next, it will tell you the total number of opcodes in the dump, and then it will list the compiled variables. We'll look at those more shortly. Finally, it will list the opcodes, one per line in the table, starting with the header row. The table columns are the line number in the source file, the opcode number, entry and exit points indicated by left or right aligned greater than signs, the opcode name, details on global variable fetches, for example, superglobals and the global keyword, extra data associated with the opcode. For example, if there is a jump opcode that will contain the number of the opcode to which it will jump to, the location where return data will be stored, and finally, the operands used by the opcode. For example, two variables to concatenate. One of the most important things to understand when reading a dump is the 4 types of variables it shows. Variables prefixed with an exclamation point are called compiled variables. These are directly tied to the variables you define in your code. Variables prefixed with a tilde are called temporary variables and are used for storage during internal operations. Variables prefixed with a $sign are another type of temporary variable. However, these are treated more like user-defined variables with ref counting. The final type of variable are prefixed with a colon. These are temporary variables specifically for the storage of class hash table lookup results. Let's start by dumping the opcodes for our sayHello method. You should note that we have a compiled variable, !0, which represents the $2 variable in our code. So let's walk through the opcodes. First, we have a receive. This is where the function receives the parameter and it is assigned to the !0 compiled variable. Next, we have addString, which creates a temporary variable identified by $0 and assigns the static part of our string, hello. Then we have addVar, which concatenates the contents of our variable, !0, to our temporary variable, $0. Finally, we echo the temporary variable, $0. To end, we return null, as there is no explicit return value. The last thing we're going to look at is the opcodes for the 2 lines of code that actually instantiate the object and call the sayHello method. Again, we have a single compiled variable, !0, which corresponds to our $greeting variable. You'll notice that we have more opcodes here. That's because while the sayHello function is more lines of code, it is only doing one simple thing, echoing a string. So, looking at the opcodes, we start by calling fetchClass to find the greeting class, and we store the result of the lookup in :1. Next, we see the new opcode, which instantiates an instance of the class as identified by :1 and assigns it to a temporary variable, $2. Then we have doFCallByName, which calls the constructor. We then assign the resulting object held in $2 to our compiled variable for $greeting, !0. For the second line of code, we start with init method call to start calling the sayHello method. We then pass in the world argument with the sendVal and call the method again using doFCallByName. Finally, because the script ended successfully, we have an implicit return of 1. I hope that this introduction has shown you the benefits of both opcode caches and an understanding of how things work under the hood. There are a number of resources available for you to look up, both as Zend opcache and APC source code repositories and PECL packages, as well as 2 great blog posts. These blog posts are Understanding Opcodes by Sarah Goldman, a core contributor to PHP, and the second is more information about using VLD for source analysis by Derek Bertans, the author of VLD. All of these resources are linked to via ey.io/opcaches. If you have any feedback or questions, please feel free to contact me via Twitter @dshafik or email davey@enginyard.com. And again, those resources are available at ey.io/opcaches.